All right, now let's move into the presentation. All right, many of you probably have heard from news about the dumped or the discarded wind turbine blades, okay? And they've been dumped in Texas, Iowa, and Minnesota. And it's a complicated story, but the bottom line is many of them just idling, sitting, and actually now they become a environmental hazards, okay? And because many of the structure are hollow, they accumulate rainwater. They are becoming the breeding grounds for mosquitoes, and for the ones in Texas and underneath the wind turbine blades, and actually it provides shades. People find actually snakes underneath. And well, what I want to say is, indeed, this really shouldn't be there. At this moment, I think the wind turbine company spent about $3,000 to pay somebody to take away a wind turbine blades. Okay, and so there were companies taking advantage of this, and they took the money and stored them near the original wind farm, and then didn't do anything. That's what is happening at this moment. And so, please, if you just do a very simple Google search, decommissioned wind turbine blades, you will find a lot of articles about the decommissioned wind turbine blades, possibly even more than the wind turbine blades in service. All right, so let's offer a little bit more background information, okay? And obviously, everybody know the energy transition is a bigger part of our economy now. And as a matter of fact, 10.8 our electricity nowadays are generated by wind energy in United States, will be 20% by 2030 and 35% by 2050. Currently, well, Texas, interestingly, generates 28.6% of wind energy in the United States. Okay, and as you know, the wind turbine blades, they're subject to very well challenging environment. They rotate, they bend during their operation. So indeed, for those challenging dynamic operation, they only have 15 to 20 years, even though some of them are designed for 25 years. But I really don't see the wind turbine blades served up to 25 years. And obviously, in recent months, you also see there was one wind turbine blade being snapped in an offshore wind farm. I believe that's offshore of near the Massachusetts. Okay. At this moment, we have 6,000 to 9,000 wind turbine blades decommissioned annually, and this will be accumulated to 4 million tons of blades waste by 2050. We really don't think these are waste, okay? But somehow at this moment, it's been treated as a waste, okay? So these are the current practice in decommissioned wind turbine blades disposal. So DWTB, you will see this I use a lot, okay? Decommissioned wind turbine blades, okay? And landfill, okay? And that you can see right there. And obviously, these are very large size. They are hollow, so it's really not very efficient for landfill. And also, they cannot degrade over the time because these composite materials, they are just built to last, okay? And as a matter of fact, in most of the European countries, it is forbidden to send wind turbine blades to landfills. And obviously, most of the European countries, they have high price for anything to go into landfill because of limited space. So next approach is incination. So, and obviously this become also a problem. Why? You have to use additional energy, right? And it generates waste. So there's a lot of problem. Okay, mechanical recycling. And So in this case, just as you can see, these are really strong material. And because these are glass fiber, as you can see here, okay, so this saw, they are diamond tipped, okay? Otherwise, the saw won't last very long. And the cutting, shredding, and this take a lot of energy. And obviously, they can be utilized as construction fillers, okay? Indeed, what we think, this is still too early to do this mechanical recycling, okay? We think we can restructure it, reuse it with another life, 25 to 50 years before you're going to do the mechanical recycling. Thermal recycling, and obviously, and as you can see, all of them involving elevated temperature. That means additional energy has to be injected, okay? And they say, well, in the research laboratory, indeed, the fiber can be recovered, but it's at a really, really high cost. As a matter of fact, if we look at this, right, and one of the company was supposed to recycle them, it claimed it has a good technology to recycle the fiber out of the blades. As a matter of fact, from the very beginning, they know that to recycle $1 of fiber, they have to spend $10. So commercially, it's really not a viable approach at this moment. Maybe in the future. Chemical recycling, once again, this also is a very costly process. Okay, and you look at these supercritical fluids like water, alcohol, and once again, at a high temperature, at a high pressure, okay, and you have to depolymerize the fibers, the matrix to recycle the fiber. Once again, it's also very high cost. At this moment, this is really not commercially possible, okay? And there's still very high cost. So what would be the best approach? And I think this is very important. As you can see here, reuse. This is especially useful for the wind turbine blades. And as I'm going to show you later on, and the wind turbine blades are really, really strong material. Even though they've been used for 20 years in dynamic situation, their life for static application will be another 25 to 50 years, okay? And obviously, we are conducting research to verify that. So our approach is to reuse. So extend the life cycle of wind turbine blades as a structure member for another 25 to 50 years. Then we can recycle it. And also we have a different way of recycle it. So for the resin, basically for the matrix, we will cut into small cylinders like that size of aggregates. So we will mix with concrete. It can significantly increase the ductility of concrete. Okay, so in this approach, nothing will go into landfill. And we don't really need to use too much energy to reuse or to form the circularity of the wind turbine blades. All right, so this is our first project, and which we have successfully built based on detailed material testing, finite element analysis. So overhead sign structures for highways. And so why we use this for such a structure? First, well, this structure has very limited load, right? In this case, as you can see, it's mostly just the load is by itself. Occasionally, it may be subject to Category 4 hurricane, right? And that's just occasional load. And we can show that indeed the structure we designed can handle 140 miles wind load, okay? So this is a structural reuse. we think we can extend this life by 50 years. Even though the dynamic life of these wind turbine blades is exhausted to rotate, that's that's just like airplane wings. It's a very, very challenging environment. However, as a static structure, the one showing here, this is not very challenging. On the other hand, many of you probably know the composite material as the one I'm showing you here. This is exactly material to build ocean-going niche boats, fiberglass. As a matter of fact, we use the same repairing kit to repair this used wind turbine blades. So these are also very feasible for coastal structures because they are anti-corrosion. Okay, they are also built to last. So we have other proposals. So they can build seawalls under the round section. The root section of the wind turbine blades, they are circular. They are really, really, really strong. Okay, they can be utilized as pipe coverage. Probably ask why they're being used as pipe coverage. The current approach, most of them, to handle large load, they use reinforced concrete structure, which involves rebar. A little bit of crack will result in severe corrosion because of the rebar. Okay, and also because of the seawater rise, a lot of structures previously are not subject to seawater now are subject to seawater, so will cause corrosion. And this can also be utilized as a coastal column. They are naturally designed as a streamlined structure. Okay, and also as I mentioned earlier, with the rise of the seawater, a lot of previously exposed fender for structures now they're submerged, which pose significant issues for these bridges. And we have seen debris like a tree impact with a bridge girder, and we also see like barges and boats impact on the bridge column, bridge fender, or bridge girder. And as a matter of fact, those composite material of wind turbine blades as a segment, they have very good energy absorption capacity. Okay, and so we go and use them as superficial layers to protect infrastructure. Other proposed idea including green space structures. Okay, the support for beach access ramp, support for recreational pier, and the playground structures. All right, so now we're going to talk about the material testing. So we have received a truckload of donation from Carbon River, and we appreciate their help. And so these are as you can see, these are the cross section of the wind turbine blades. And we conducted a variety of testing, okay? And as you can see, in this case, these are the resin, this is a matrix, this is wood, okay? And why you probably ask why they use wood. In this case, this is a very lightweight balsa wood, and mainly to help to increase the bending stiffness, okay? So we have conducted series of testings, okay? Longitudinal tensile testing and the transverse tension tests, okay? And we also have done compression tests, okay, as you can see right there. Okay, so we compared our test results with others. So indeed, we can actually confirm this material, even though they are out of a wind turbine blades already been in service for around 15 years, they still have a superb materials properties. I'm just going to show you a slide, okay, from my dear colleague, Dr. Mo. And this will be more obviously for you to see. Compressive strength of concrete 4 KSI. versus 24 KSI of decommissioned wind turbine blades. You see, this is much stronger than concrete. Longitudinal tension test, we compare to that of steel rebar, 60 KSI. And for the wind turbine blades specimen, 71.5 KSI. Okay, this is bending, okay, and deflection. And concrete, for the commonly used 4 KSI concrete, that's 500 PSI. For the decommissioned wind turbine blades, 3,358 PSI. That's about more than 6 times better than concrete. So basically the conclusion here is decommissioned wind turbine blades has better material properties than concrete and steel. It is just such a waste to throw them away or to discard them. Indeed, they can be utilized for many, many applications, as I just point out. They are naturally anti-corrosion. They can be utilized for coastal structures, especially Houston, close to the coastal, and Galveston is a coastal city, and they're subject to a variety of challenges due to rise of the seawater level. Indeed, we also conducted foresight testing. This is the largest test ever in the world done on decommissioned wind turbine blades, and 25 foot long, okay? And once again, I wanted to thank Dr. Mo and the 2 students, Nagesh and Boo, for conducting this experiment, and also the support from ETI to enable this much needed research. So this is the data acquisition system. This is the setup, okay? So this is, as you can see, this is edgewise orientation. And this is a bending test, and these are the actuators. I believe this actuators is the loading capacity, I believe, is about 100 ton, I believe. All right, so these are the testing curve, okay? And so this is the initial stage. So we can see initial of the shear crack at the support, okay? And here is, we see more shear failure in this. So throughout the test, actually, the main damage are at the support. That means if we have better support, if we have larger loading area, actually, we will see much better results, okay? So indeed, these are just the superb, strong materials, okay? All right, we also conduct the test in the lateral, in the flap-wise, okay? As you can see, once again, this is the largest testing of a decommissioned wind turbine. This is a flap-wise orientation. So this is a 33 kips, very strong. We do see the delamination between the web and the blades, the shear web and the shell, okay? But this is really strong materials. So the results are for the testing, I just going to keep it short. These are superb materials, okay? Are extremely strong, no matter from the material testing or from the structure testing. They can be utilized in many different applications. Indeed, to increase the bending strength of the structure, since the decommissioned wind turbine blades, they are hollow structure. We can fulfill the inside with, for example, if it's a lightweight, low cost, expanding form, all right? We can fulfill the inside with light concrete. We can fulfill inside with regular concrete. If that's the case, we will significantly increase its both flexure capacity, loading capacity, at edge-wise, and also at the flap-wise. All right, so we got all these interesting materials properties. Now we can build finite elements. And so, as I said, the overhead sign structures, before we build, we performed detailed structure analysis, just to make sure indeed these are very strong materials. And we did self-weight analysis, and we did wind load analysis, okay? And 140 miles per hour wind load, okay? And so this is the finite element result. This is a model analysis. As you can see, this is the first model of the structure. Is at 3.43 hertz. And this is the second animation. This is the view of the second mode. And this is the third mode. So the third mode is 10.54. And now we can see the second mode and the first mode are relatively low frequency, okay? 3.43 is 3.49. And obviously, this depends on the wind direction. If wind blows from this direction, most likely mode 1 will be excited. If wind blows this direction laterally, and this is how the structure will oscillate, will vibrate. And obviously the second mode will be excited. All right, this is a self-weight analysis, and you can see there was only 0.04 inch deflection at the center, so it's really negligible, okay? And this is the geometry of this overhead sign structure, 40 feet across, okay, and 20 feet high. And so why we use this is a standard, okay, we're following, and this will cover 2 lanes of highway traffic with 2 shoulders, and the clearance will be more than 16 feet, and that is the minimum, most of the minimum clearance required for highway. All right, and we can see this is a self-weight plus wind load analysis, okay? And in this case, you can see out of a plane deflection at the 140 miles per hour wind speed is 3.4 inches. Compare, this is a 40 feet wide structure, so it's really very small deflation. And keeping in mind, this blade, just like an aeroplane wings, they are flexible. So 3.5 inch deflection is really nothing, okay? And other deflection are very, very small. There's no need to worry, okay? And obviously, so this gives us confidence our structure is sound, even in case of 140 miles per hour wind speed. All right, so pretty much we followed the AASHTO, that's American Association of State Transportation Office, for the design of this overhead sign structure, okay? And as you can see, these are the wind turbine blades we received. They may not exactly fit our purpose, so we have to do a little bit of trimming, cutting, and the cleaning, okay? So you can see this is the right column, left column, horizontal member, okay? this is what been donated to us from the laydown yard. Okay, and there were some delaminations, so we repaired them. Okay, and at a relatively low cost. We used exactly the same repairing kit that are utilized to repair basically leisure for the ocean-going leisure boats. Okay, and we have painted. Painting is very important. This mainly is to offer protection to the matrix beneath it. So the painting is very important. And we also followed the codes and the foundation. Okay, the foundation, obviously, it's very important, especially when such high structure are subject to 140 miles per hour wind speed. Okay, and so we followed once again the design code. Okay, and one of the Department of Transportation's text code. All right, so as you can see, we use drilled shaft, okay, and we have a steel cage. Even though this rebar we exactly followed the code, however, we think this is a little bit overdone. The reason is our structure is much lighter than the traditional concrete or steel structure. Okay, so in the future, I believe we can reduce the amount of rebar used. Okay, we can also reduce the amount of rebar used here. This is the pile cap. Okay, so as you can see, this is the cap sit on top of a foundation. Okay, and we also collected the concrete specimen for structural testing to ensure the concrete is up to standard. And these are the ankle bolts we embedded into the structure, okay, prior to the casting of the concrete. As you can see, this is casting of the concrete, pouring of the concrete. So these are the anchor bolts for the wind turbine blades, and we also performed the test, and actually all the concrete are actually more than the strength is more than been specified. And obviously, the connection is really important. We actually adopt a very simple design, L brackets and nuts and bolts. And for the location, we cannot have access to the inside, to the other side of the structure. We use blind bolt. Okay, so how the blind bolt work is, so basically you rotate it to one direction. So as you can see, this piece will basically rotate and form as an anchor point, so we can apply load right here. So that's two types of bolts we used: A3025 structure bolts and M16 blind bolts. Okay. All right, so this shows the construction process. Okay, and so this is the column member. So this is right column, left column, being put into state location. Lifting of the horizontal member. And we want to point out this structure compared to steel structure, it's significantly lighter. And therefore, basically, you don't need to use a heavy dedicated crane, okay? And so this is lifting, installation of the sign structure. Okay, as you can see, the connection, we spend a lot of time to analyze the connection design. And finally, we chose, as I said earlier, this L bracket. The reason is it's just so simple to use. Since along this part, we cannot access the inside, we use blind bolts, okay? So these are the L bracket is being used out through for the foundation, also to connecting the vertical member with the horizontal member. So as you can see, this is the foundation. So, and this is a bracket actually installed on the sign to hold the traffic sign structure. All right, so this is the constructed product overhead sign structure with a clearance of 16 feet with a width of 40 feet. Okay, and I would like to point out, so this structure already, since the erection of this structure, I believe is late April, early May, we already experienced two major events. Okay, the first one is on May 17, tornado around downtown and also UH, peak wind gusts 80 miles per hour. And obviously, the barrel. The barrel caused a lot of damage to Houston metropolitan Houston area. And these are the trees down. These are the fence next to the structure. These are not far away from the structure. And our structure after this wind gust of 100 miles per hour is intact. Okay, there is no damage at all. So this speaks the structural resilience of this structure. Okay. All right, so what's the cost saving? So at this moment, the wind turbine blades is free for us, even though we have to pay for the shipping and handling, which at a small quantity is relatively expensive. But I think if we can do mass transportation, it will be much cheaper. Okay, and so we do have quite a few partners to work with us in donating wind turbine blades to us. So in this case, we compare to exactly the same structure, all steel structure. So basically, we don't need to pay for the materials, and it ends up they have a saving of 73%. Okay. However, we still need to pay for installation, and also we have to pay for the foundation and so on. Okay, but it's 73%. And the most importantly, it's environmental benefits. Okay, and you can see for this 40-foot span OSS, overhead sign structure, we eliminate CO2 emission by 242 tons. Okay, and so this is really, really a powerful message. Not only we saving money, and we are also saving the world. Okay, and once again, we are writing proposals, try to study, establish a model to find the useful static life of decommissioned wind turbine blades for applications like this, which is a static application. So in most cases, it's not subject to any load, all right, except itself. Occasionally, it's subject to very severe, violent load, such as that caused by Hurricane Beryl, right? But this is unlike how this used to be. It's rotating. That's very severe loading condition. And some of the wind turbine blades, you look at they rotate really slowly, right? But actually at the tip, it's almost supersonic speed. So it's a very challenging environment. All right. In addition to our research, we also spend a lot of time on training. And Dr. Mo innovatively integrated this design into the capstone design at the in civil engineering. So students designed the two structures, overhead sign structures. Okay, they have a detailed analysis, drawings. So two teams work on the overhead sign structures. This is one of their design projects. And another team working on the pedestrian bridge, okay? And many of you probably noticed this, there was original wooden bridge on that, right? And that wooden bridge collapsed about 1 month or 2 months ago because, as you know, the wood is really not very good to handle weather and handle corrosion. And so this is our design using decommissioned wind turbine blades, okay? And we believe this will survive for another 25 and 50 years, okay? With proper maintenance, the major maintenance, just painting. And the bridge design actually has already been incorporated in, this is in Ireland. So this is one of the bridge, but and I think we can do much better job. Okay, so there's no need to involve the root section. Okay, and so this is our design. This is a detailed design. Okay, as you can see, and once again we use L bracket. Well, not exactly L bracket. So this is with a little bit of support. Okay, so it's still very, I would say, inexpensive cost, and this would have, this bridge, I think, would have 25 to 50 years lifespan. All right, so now I move into the conclusion. So the decommissioned wind turbine blades, they are really, really strong material, okay? On material level, they are stronger than both concrete and steel. At system level or at the structure level, they are super strong, and they can be their strength can be further strengthened by fulfill different material inside the hollow space, okay? And we have many different visions, okay, views for the wind turbine blades, as I have presented. They can, especially they will be very helpful as coastal structures because these materials are basically inert to erosion, corrosion, and they are very robust, they are very durable, and there's a lot of opportunity we can use. So after another 25 to 50 years service as a structure member, they can be decommissioned again, and then their matrix can be cut down to the cylindric shape like that of aggregates. They will be mixed with concrete. Indeed, we can form the circularity for wind turbine blades, which I think is very important for wind energy. If we cannot recycle or we cannot recycle the wind turbine blades properly, we cannot say the wind energy is truly green energy. That's the end of my presentation.
Thank you very much, Dr. Song. This is one of our flagship projects at the UHETI, and thank you for recognizing us on that sign. We do have a few questions and comments in the chat. So, John, if you want to unmute yourself and ask the question, I'll give you a minute, or I can ask the question on my end.
Should I look at the chat right now?
It's best if you look at the chat, please. Yes. I mean, I can ask the question, but it's clear in the chat. I hope.
Okay, sure,
I can
will.
offer clarification.
Yeah.
All right, I'd be happy to attend that remade conference on April 10 to 11. Where is that conference?
So the remade conference is in DC. But the question that John has put in the chat is that, is there an estimate of the fraction of the DWTB that can be used for supporting highway signs? In other words, is the market large enough to absorb the decommissioned volumes?
As a matter of fact, I think my view is when this goes on, instead of pay somebody to haul away the wind turbine blades, I believe the wind farms can sell these blades at $2,000 or $3,000 a piece because they are valuable construction materials. And yes, there's a big enough market, but there is a lot of hurdle because once we get into a new market, this is a disruptor, right? We are disrupting the existing practicing of overhead sign structure. There is a lot of actually problem with the existing overhead sign structure. They are so rigid. And if a driver bump their vehicle into the steel foundation or the concrete foundation, most likely the driver will be severely hurt or sometimes result in fatality. And I have seen that case, okay, which is reported by TxDOT. Versus the concrete support, versus the decommissioned wind turbine blades. These are really good energy absorption material. They will stop the vehicle in a gentle way by absorbing the energy, okay? Yes, the Carbon River is our partner. Actually, they donate us with the wind turbine blades. Indeed, at this moment, there is a way to recycle the fiber from decommissioned wind turbine blades. I think the main issue is the cost, and then also the quality of those fiber.
Thank you. If there is any other question, you can definitely contact us or Dr. Song directly. But this is a very interesting project that we are supporting, and we are really proud of the outcomes that have come out of it. Thank you very much, Dr. Song.
Yeah,
for
and also want
presenting.
to say is even after 25 or 50 years of service as a static member, at that time, it is decommissioned. Well, if there was an inexpensive way to recycle the fiber can still be recycled. But think about, we give another new life to the structure, 25 to 50 years.
Yeah. And I think one of the points that this work has highlighted is that you are not modeling or you are using the same structural properties that it was initially built with,
Yes.
which is the core of circular economy, that you will keep things in use as it was intended for as long as possible. So that really gives this a different look towards repurposing these wind turbine blades for the purposes of the structural strengths that it provides. So I think
And
that's
we welcome anyone who are interested to see this. Please come to see it. And
Yes.
this is a self-reinforcing structure. Even though we fixed some of the minor damage, as a matter of fact, even we don't need to fix it. It will be self-reinforcing. And so this is especially this structure, the current structure is extremely strong. So,
Yeah.
and we welcome you to see it, and we welcome you if there's any way you can adopt this into your design. You are very welcome to collaborate with us.